recognize this function from last time. It's a function that's continuous nowhere. It's 1 if x is rational, 0 if x is irrational. So it's just a sprinkling of dots everywhere. It is a function because it passes the vertical line test. So that means that it's continuous absolutely nowhere because the limit of some sequence that's leading up to an output, it's just never going to be that output itself. Or in other words, the limit at x approaches c of f of x is never equal to f of c. So here we've got it continuous at only one point because we have x if x is rational, 1 if x is irrational, so it's continuous at x equals 1. Here we have it continuous at 2 points. Here we have it continuous at infinite points, but over an unbounded amount of time, like from 0 to infinity, for example. But if we only do it from, say, pi to 2 pi, then we've only got 1 or 2 points of intersection. However, if we want something that is always infinitely continuous and discontinuous every point in time, we can look to this function, 1 if x is 0, 1 over n if x can be expressed as m over n in lowest terms, 0 if x is irrational. So we've got this, which is continuous and discontinuous everywhere, continuous at any rational number and discontinuous at any irrational number. Now we've got the concept of an actual functional limit, the limit of a function as it approaches c, using this epsilon delta definition. So we can be solving for epsilon using this formal method here, which looks quite similar to our sequence method from a long time ago. We have that if the absolute value of x minus c is less than epsilon, the distance from f of x to L has to be is less than delta. The distance from f of x to L is less than epsilon. And so this is a little bit harder when our graph has a non-constant slope like y equals x squared.
What do you see?
Sand.
Imagine if we could look so closely, we could see each grain, each particle. You see, there are patterns in everything.
Integrals, infinite series.
I've never seen anything like them. From an Indian